Hi everyone, my name is Nusha and I'm presenting Vision Transformer Part 1. In this presentation, first I'll give a review of Transformer just to remember the architecture. Then I'll go through a series of methods that utilize Transformer in Vision domain. The papers that I'm going to talk about is Image GPT, now Vision Transformer, DIT, and Swing Transformer. I've tried to organize these papers based on the year that they were published, so each model would be related to the one before that. We saw transformer architecture many times in this course before. It contains an encoder and a decoder. Each of these components can be repeated n times. The most important component in this whole architecture is multi-head attention, also known as MSA. MSA works with three vectors, values, keys, and queries. And that's how it will calculate the attention based on these three vectors and the input. The mechanism of this architecture is completely discussed in this course before, so I'm not going to go into more details. I'm just going to move on. I just want to mention that for vision transformer, we're only going to use the encoder. We don't need the decoder. For example, in NLP domain, when we want to translate a sentence, we pass, for example, an English sentence to the encoder, we get the embedding, and then we pass the embedding to the decoder, and then translate it to another sentence. But in vision domain, we just want to get the embedding from the images, and then we can use these embeddings for downstream tasks like classification. Transformers are very successful in NLP domain, and that's what inspired people to use the idea of transformers in vision domain. ImageGPT was one of the first papers suggested by OpenAI that utilized the architecture of transformer for images. And shortly after that, Vision Transformer was suggested by Google. This approach was really successful, and also it increased a lot of interest in using Transformer in Vision. Actually, the other papers that I'm going to talk about were inspired by this VIT, or Vision Transformer. Now, as you can imagine, one of the fundamental challenges of using transformers in vision domain is to how to create a sequence from an image. We know that transformers cannot take an image as an input, which means that we have to turn an image into a sequence. Each of the papers that I'm going to talk about will overcome this challenge in their own ways. So, like I said, one of the first papers in utilizing transformer in vision is generative pre-training from pixels, also known as ImageGPT. This architecture, as you can see, it contains three components. The first component is the pre-processing, which will transfer an image into a sequence. The second component is pre-training, which train two models. The backbone of these models are GPT-2, and they're the same, but these two models are just trained with two different objectives. And the third component, which is also the last one, will evaluate these models. I will explain each of these components in more details. The first component, which is the pre-processing, it will convert an image into a sequence by reordering the pixels. Now, an image from ImageNet dataset has a dimension of 224 by 224 by 3, which is like the number of channels, which is more than 150,000 pixels. This is a huge sequence. If we want to reorder the image to create a sequence, that will be a really long sequence. That's why ImageGPT used context reduction, which has two steps. The first step resizes the image into a lower resolution. It will turn it in 32 by 32 by 3. And then there's another step, which they use a customized color palette to change the RGB. So they change that the number of channels of 3 to 1, and now they have reduced the dimension from 150,000 pixels, more than 150,000 pixels, to 1,000 pixels. So just to look how it works, this is an image from ImageNet. They make the resolution lower, and then they change the RGB, as you can see here. And then they reorder these pixels in the way that these arrows show. They put them together and create a sequence. Okay, so after creating the sequence, there is a component for pre-training. Again, they are using GPT-2 architecture with one of the two objectives. First objective is autoregressive, which also known as next pixel prediction, and the other one is BERT, which is mask pixel prediction. Okay, so let's talk about autoregressive first. This is how it works. Imagine you have a data set, which here will be a data set of images. Consider a data from this data set, which will be a sample of image. This image, which we're going to know it as X, will contain a sequence of pixels. Now, the probability of this image or this sample will be based on the probabilities of the pixels that created this sample. And the probability of each pixel will be based on the given or the observed pixels. Now, ImageGPT use identity permutation, which means that it doesn't reorder the observed pixels. In other words, the probability of pixel I will be based on the probability of pixel 1 to I minus 1, or the observed pixels for this pixel will be 1 to I minus 1. So it's like no reordering here. But autoregressive in NLP can use reordering. It's just in ImageGPT, it doesn't use any reordering. Okay, so now we know how to calculate the probability. We can train the model by minimizing the negative log likelihood. So looking at this loss, you can see that the model is trying to make sure that the probability of the image sample will be as high as possible. So the loss will be near zero. The other objective is BERT, which is mask pixel prediction. So for BERT, first we consider a subsequence from all pixels, which is, we're going to call it M. The probability of each pixel appear in M will be 0.15, and the pixels that will appear in M will be masked during the training. That's why we call M the BERT mask. So during the training process, we will try to minimize this loss, which is this loss function is predicting masked elements based on the unmasked ones. Now, just to sum it up and visualize both of these objectives, for autoregressive, for example, this is the input. We want to predict this pixel in the sequence, and these are the observed sequence. So in each step, each pixel will be predicted based on the previous observed pixels. So for example, look at this blue one. You can see that it is based on the previous observed ones, or this red one is based on the previous observed ones, and so on. So at the end, the pixel will be predicted using all these other observed pixels. So this is how autoregressive predict a pixel. The probability of this pixel, the last one that we predicted now, will be dependent on all the other observed ones. For BERT, this is the input sequence. Now, imagine 2 pixels are masked. Now, they're going to be predicted based on all the other observed ones. So look at this blue one here, okay? This blue one, the probability of this will be calculated based on all the other observed pixels. So you see, it's like everybody, not just the one before that pixel. And so on, so as the red one here. And these two pixels will be created. So the probability of these two pixels will be calculated independent from each other. While you saw that in autoregressive process, each pixel was predicted actually based on the previous ones. Okay, so for evaluation, they either do fine tuning or linear prob. For fine tuning, they add a classification head at the end of the representation at the last layer. It will be here in this image. And then they will train both the transformer and the classifier together. So the loss will be based on the loss of classifier and the loss of the model, which can be either autoregressive or BERT. For linear prop, they do add the classifier to the representation, but they only train the classifier and freeze the transformer model. So this will be only trained based on the loss of classifier. Now for this process, since they don't want to train the transformer, they can add the classifier to each layer that they want. They can add it to the last layer or in the intermediate layers or to the first ones. And for the result, that's exactly what they did. For autoregressive that is pre-trained on ImageNet, they applied linear prop, or they applied the classifier to different layers and they report the accuracy. So you can see that it's amazing that the result for the intermediate layer is actually better than the last layer. Well, the reason is that in a transformer, the first layers will not contain a lot of information, and the last layers will be so specific to that pixel that the model is trying to predict. That's why the intermediate layer may contain more global information, and the result will be better in, for example, classification in these layers. For fine-tuning evaluation, you can see that the accuracy is relatively good for CFAR 10 and also CFAR 100. But for example, in CFAR 100, if you see EfficientNet, which is a CNN-based model, actually performs better. This is also a general result on two objectives, and for two data sets. So this is BERT and autoregressive for CFAR 10. These models were pre-trained on ImageNet, and these are the results for ImageNet, and they were pre-trained on some web images. So until here, they're both pre-trained. Here, for example, in this picture, they are pre-trained on ImageNet. Then they apply linear prop to increase the accuracy. And then after that, they apply fine tuning to, again, increase the accuracy more. And you can see for CFAR 10, they reach 99%, but for ImageNet, the best they can do is like near 68%. And this dark part that you see on BERT, it's like they apply an ensembling process just to, further improve the accuracy as well. Here are some visual results for ImageGPT, and I think they're very interesting. The last column here, it's like the real input, the target one. And the first one here is like the masked pictures. And for example, look at this first one, which is an image of a cat. Half of this picture is masked, but still these intermediate pictures that you can see, there are the ones that the model predicted. They're quite well, and I mean, look at this one. It's it's kind of funny. Or for example, these birds, you can see how the model actually performed. So it's quite impressive how this model actually works very good. Okay, so we saw how ImageGPT works, and there is a main problem with this model. They resize the images to 32 by 32, so they lose many details from the information. They're just making a huge image with a lot of details into a very small, low resolution image. VIT solved this problem by creating sequence from patches instead of the whole picture. Again, this paper was very successful, and many other papers used this idea in their research. Here's the overall architecture of VIT. The main idea is using patches instead of large images. I will explain the process. So yeah, I will explain the pre-process here. But in this slide, I just want to mention that the transformer encoder is the same as transformer. They didn't make any changes to the architecture. They just add an MLP head here for classification, just to find the class of the image. Okay, this is how VIT works. First, they split an image into patches. So imagine we have this image, they split this into patches, P by 3 because of the number of channels. They mentioned that the size of the patches that they usually use is 16. And then they put these patches next to each other. You see it would look like this. And then they put the position of these patches beside them as well. So this is patch 1, 2, 3, 4, 5, 6, and so on. Okay, so each of these patches will be turned into a sequence based on their pixel. So the length of this sequence will be P by 3. Then this sequence go through a linear projection. This linear projection only changed the dimension from this P by C to D. On the other hand, there is a position embedding. So this position of the patches go through position embedding. This will convert the integer into a d-dimension vector. Then these two vectors will be added together, and they will create they will be the pre-process step for this patch. This process will go on for all the patches. Okay, now before passing this to the transformer, they add a trainable vector at the beginning of this sequence. They call this CLS token. So CLS token, this pink one that you see here is a trainable vector, and this purple one is actually position embedding for 0, because patches started from 1, and this is the position 0. Now this whole sequence will go through the transformer. Yeah, so this is the input, the CLS token, the patches that went through linear projection, and then they were added with the positions. Well, the transformer contains layers, and then the output, the last output actually of the transformer, the part of this output that it is related to the CLS token, which we're going to call it Z0L, will go through this MLP head, and then label will be created. Okay, so here are some results. VIT actually outperforms CNN-based models. Here you can see that they trained their model actually on a data set which is called GFD. This data set contains 300 million data for training, and it's not publicly available. It's like Google's private data set. They train their model on that. This is like training with patch of 14, patch of 16, and this is like training on another data set. So compared to CNN-based models like ResNet and EfficientNet, you can see that the accuracy is better. On the other hand, VIT is much faster than CNN-based models, you can see here. This is also another result that you can see. There's a data set called VTAB. It has different tasks. So based on this picture, you can see that VIT actually outperforms other state-of-the-art models on each of these tasks. Here are also some visualized results. We can see the power of VIT with these pictures. So the first picture here applied PCA to the output of linear projection. So they changed the dimension from D to 28. And then they showed these results in 28 pictures, images here. So these pictures are very similar to the feature extraction pictures that are created by CNN models. The second picture here shows the performance of the position embedding. So they actually calculate the cosine similarity between each position embedding and the rest of the position. You can see that the similarity is higher in the same row and column for each position. And the last picture here actually shows the mean attention distance for each attention head in each layer. So each of these points shows the mean attention distance for a head. Now, these are the layers. This picture shows us that as we go towards the layer, this distance increases among all of the heads, which it means that the more global feature is extracted by the last layers. Okay, so the next paper is DIT. VIT performs very well, but it has a huge problem. The data set that they use to train this model is not publicly available. Also, it's a huge data set. It contains 300 million data for training, which is something that Google can train in their GPUs. DIT, which is suggested by Facebook, use a distillation process to actually solve this problem. And they use ImageNet, which is 10 times smaller. Okay, so before we understand the architecture of DIT, let's just go through the idea of knowledge distillation. So in knowledge distillation, there is a pre-trained teacher network, and then there's a student network, which is usually smaller than the teacher, and it tries to mimic the behavior of the teacher network. In other words, in the training, we will try to distill the knowledge of the teacher to the student. This distillation can be done in two ways, soft distillation and hard distillation. For soft distillation, the student tries to recreate the distribution predicted by the teacher, but for hard distillation, the student tries to recreate the labels predicted by the teacher. So looking at this soft distillation here, the first term is cross entropy based on the student prediction and the true labels. And the second term here is KL divergence between the prediction of the student and the teacher so that it will increase the similarity between these two networks. Or in other words, it will try to make sure that the student will behave similar as teacher. For hard distillation, the first term is like the same based on the true label, like the output of the student network and the true label. The second term here is the output of the student network and the teacher label, which, like I said, the student will try to recreate the labels that the teacher predicted. So for understanding DIT, let's just say that it's very similar to VIT. So you remember VIT architecture. It's the same process. So we'll turn an image into patches. These patches go through a linear projection. There's also an position embedding layer that will embed these position of these patches. And this sequence will be created the same. The CLS token is the same. This will be added at the beginning. Now, here's the first difference. DIT also has another token, which is called distillation token. It will be added at the end of this sequence, but it is same as CLS. It's a trainable token. It's a trainable vector. Okay, so this sequence goes through the transformer encoder, and then there will be two MLP heads. The first one is the same as the one in VIT. It takes the CLS token and the true label. It calculates the cross entropy loss. The other MLP actually create another loss, and this transformer model will be trained based on both of these losses. Okay, so there is a teacher model here. The teacher model that they use is CNN-based model. So this picture will go through this CNN-based model as a whole. They don't need this sequence. This will go through this teacher, and teacher will give a prediction. Now this MLP will use the distillation token as the input and also the prediction of the teacher, or will consider the distribution of the teacher and then calculate the loss of teacher. So this transformer, which is a student network in this scenario, will be trained based on these two losses. For training, they use data augmentation such as RAND augment and COT-MIX. There are other augmentations as well. These are just two examples. RAND augment is like changing the contrast or rotate the picture or change the brightness. For COT-MIX, it's like you have a picture of a dog and then a picture of a cat, and then you combine them together. They also introduced variant architecture based on the number of heads and the number of layers, and their embedding dimensions is different. DIT-B, the one that you see here, is the architecture of this one is similar to VIT. They also mentioned that in some results that we'll see, they fine-tuned the model on the same dataset, but they changed the resolution of the pictures to 384. So for teacher network, they use different models. All of these models are CNN-based model. The bigger CNN model actually performs better. This is the accuracy of the model. This is the accuracy of the student network that it is pre-trained. And this is the accuracy after applying fine-tuning with those pictures, which I mentioned. They reported the result for different distillation strategies. So this symbol that you see here, it means that the IT used two losses, the cross entropy loss and the teacher loss. But here, this one here, it means that it will only use one loss and not the distillation token. So the first one is trained like based on true labels without any distillation. For the second one, is like train CLS based on soft distillation. The third one is train CLS based on hard distillation. Now, these three consider distillation token as well as the CLS token. But for the first row, you see that they pass CLS token to both MLP heads. For the second row, they pass the distillation token to both MLP heads, and the last one is the same as we discussed. It's like the CLS token goes through one MLP and distillation token goes through another MLP head. It's like the original idea. And you see that this one outperforms everyone. Also, you can see from here that using distillation performs actually better than using just the true labels. This is the final result of comparing with CNN models, ResNet, and EfficientNet. This table shows that you see with the same number of parameter between DIT and a CNN-based model, DIT performs much faster. You can see that the throughput is 85.8, but for CNN base is like 25.2, while the accuracy is same. And here's the final comparison of DIT with EfficientNet and VIT. So you can see here that VIT is slow and it has low accuracy compared to the other models. DIT is same as VIT, is just trained on a data starving regime, but you can see that it is better than VIT, but not better than EfficientNet. DIT with distillation actually outperforms the CNN-based model. Also, for example, consider this image per second. You can see that in this point, with the same speed, DIT actually performs better than the rest. The last paper that I'm going to talk about is Swing Transformer suggested by Microsoft. The actual name of this paper is Hierarchical Vision Transformer using Shifted Windows. That's where SWIN comes from. Well, VIT's computational complexity is quadratic to the image size. And Swing Transformer tries to address this issue by introducing two blocks, patch merging and Swing Transformer. This is the overall architecture, and these are the components. I will go through each of them. Now, this is an image, H by W by three channels. The first component that this image goes through is patch partition. As you can imagine, this component will only make patches. So each of these patches will be 4 by 4 by 3. So the dimension of this patch is 48. And the number of patches will be H divided by 4, W divided by 4. Now, the next component is linear embedding. This image with these patches goes through this linear embedding layer. And this linear embedding will change the dimension of these patches from 48 to C. So that's the only change that linear embedding makes. And the number of patches will be the same. Okay, so now we move to the Swing Transformer block here. Swing Transformer contains two subunits. Each unit is identical to Transformer architecture. They just replace the MSA in the first unit with window MSA and in the second subunit with shifted window MSA. Let's talk about window MSA first. So this is just like the window MSA works exactly like MSA. It just consider windows, for example, windows of size 4 by 4, and then it calculates the attention within these windows. So that's the change that window MSA makes. And since now window size is fixed, the complexity is linear with respect to the number of patches. Now, there's an obvious problem with this method. As you can imagine, for example, there's a dog here in the middle of this picture. Now, while window MSA is calculating attention, there will be no attention between different windows. So we know that this pixel is related to this one, but while calculating window MSA, there will be no attention between them. So this is the problem, lack of attention between different windows, and that's why they introduced the second subunit. Before saying how shifted window MSA works, let's try this. To solve this limitation, we will shift the windows by half of the size of this window. So we move this window by 2 by 2 here, and then here, and then here, and then here. Now, the problem is solved if the dog is in the middle of the picture or anything that it is in the middle of the picture will be preserved. But here's a new problem. Instead of calculating the attention in 4 windows, now we have to calculate the attention in 9 windows. So we wanted to reduce the computational complexity, but we accidentally add some windows. Also, here's another problem. What do we do with this white space? Do we add padding? So this is the idea of shifted window MSA. They shift the window in one direction. Now this green part here moves here. This pink one moves here, and this yellow part moves here. Okay, so this will be like a reordered image, and then they calculate MSA for the windows in this new image. But here's something that we should consider. By reordering this image, we created some relation between pixels that they originally did not exist in the original image. So for calculating the attention, they consider mask MSA. And then at the end, they use reverse cycle shift just to, reorder the image as it was. So this will be the 2 subunit of swim transformer. After that, this output goes through patch merging. So the input for patch merging will be H divided by 4 by W divided by 4 by C, because this is what it was before. And we know that swim transformer, which is like transformer, does not change the dimensions. Now, patch merging, again, will define windows. Now we will consider windows, for example, 2 by 2. It will concatenate the pixels within the windows. So within each window, they put the pixels together like this. So after this process, the output will be H divided by 8, W divided by 8 by 4C, because the dimension of each of them were C. Now this is 4C. This goes through a linear embedding layer. This linear embedding will change the dimension from 4C to 2C. And that will be the input of the second swing transformer block. And so on. So this process goes on until for 4 stages that you see here. Now, we can use the output of this model for different tasks. For image classification, we can use the last output. And for object detection and image segmentation, we can use the output of all these stages. Also, you may see some numbers here. These shows the swing variance, so there will be some different swings. The difference between them is based on the number of these layers. Like, for example, swing T will be 2262, but swing L will be 22182. Also, another difference between these variants is the dimension of C. This last one, swing L, as you can see here, compared to VIT and another transformer architecture, use less flops and it is faster. Look at it compared to VIT, it's faster and its accuracy is better. This shows the same result with more models. Now let's compare Swin with, let's compare these 4 red blocks. So the image size for these blocks is the same or similar to each other. You see that compared to other transformer models, Swin use less flops, although it's bigger compared to EfficientNet. It's faster than other transformer models, but again, it is not, it's like slower than EfficientNet or CNN-based model, but the accuracy of Swin is better than CNN-based models. Like, it's better than EfficientNet. And also it is also better than other transformer. And this shows the power of Swin transformer. It used less flops compared to other transformers. Actually, it used less flops. It's faster and it also has a better accuracy.